All right, guys, we're going to get started. First thing we're going to do is we're going to do a little bit of background knowledge. So what I want you to do is get your whiteboards out, make sure you got your marker out, and listen. Some of these questions you might not know the answer to because most of the people here at school are getting all this stuff. So I'm going to try to start, just like Caleb said this morning. I was thinking about this last night. I was like, man, I'm going to record my live lessons at school so that the kids at home can get my live lessons and they will get everything everybody at school is getting. So I'm going to give this a shot, see if it works today. Hopefully it will, and then hopefully we'll be all on the same page then, and y'all won't be a little bit behind. Okay, so what we're going to do is I'm going to give you a little bit of whiteboard trivia, and then we're going to go over a couple of the terms we went over yesterday. We're going to watch some videos. So I'm going to try to hit home some of the things we talked about yesterday. I got some cool videos I'm going to show you as well. I think you'll like them. One of them's kind of like 5 minutes long. It's kind of crazy looking, so we're going to talk about it a little bit. First things first, who was the man who theorized about gravity, found out that all white light contained all 7 primary colors, and wrote the 3 laws of motion? Please write his name down, or you can write his initials down, which I do quite often. It is Sir Isaac Newton. And remember, his name was not Sir. He was from Europe, and that's what they do to royalty, is they give you the name of Sir if you've done something really prolific in your life, and being the greatest scientist of all time, probably, which nobody knew that back in the day. Proved for him to get the name Sir. So second thing I want to talk about, Newton's first law of motion is inertia, okay? And I want you to write down what I say. Well, don't write down what I say, but finish what I'm saying. All objects in motion must have what to slow them down? And if you really want to impress me, write down the 2 things that can slow objects down on Earth. And that would really impress me because that is not an easy question. All things in motion have to have what to make them come to a stop? What do they have to have? All right. They have to have a force, and a force on Earth would be gravity and friction. Those are the 2 main stoppers of objects. Now, which one of these is the major stopper of objects? Is it going to be gravity or is it friction? Circle it or write it down. Which one does most of the work we talked about? And the reason I'm telling you this is because I see this question a lot, a whole lot. It's friction. Friction is the main stopper of objects on Earth, okay? Like the soccer ball rolling across the field, the basketball coming to rest on the blacktop, the baseball rolling to a stop. Friction is the main one. Gravity plays a role in it, though, so don't forget about that, all right? Now, yes, sir?
I have a question for acceleration.
Well, let's wait until we get the acceleration, kiddo, and I promise you we will do that, all right? What is a force? Okay, I know all of us have watched Star Wars, but what's a force? What is a force? And you are doing this right now as you write down what it is. It is a push or a pull. And I want you to think about this for a minute. I'm pushing my writing implement up. I'm pulling it down. You push and pull all day long. You pull your shoelaces tight. You do so much pushing and pulling throughout the day, it'd be impossible for you to count how many times you push and pull something. All right. Now, we just talked about this incredible force. Aiden, pay attention. We just talked about this incredible force, friction. All right. And all of us have encountered friction at one time or another, whether we have been running through the house and slid across the carpet or slid across a hardwood floor and it kind of caught us and it gave us a little strawberry. Well, that's friction. The carpet went one way and your body was going the other way. And that's what caused this raspberry or this strawberry or whatever you want to call it to form. So what are the two things that friction does to all objects? Two things, all right, two things. And if you just get one, I'll be super happy. I've already given you the answer for one of them. All right, out there in TV land, let's see what you got. The first one I have is, I can't read it, heats things up. Okay, and we're going to look at a great example of things getting heated up today from friction. And it also slows things down, which is we're going to see that as well today. And I'm going to use a worldly example of friction. I'm not just going to talk about, hey, look at the soccer ball coming to a rest on the soccer field. Wow. We're going to use a worldly example today, and you're going to see what I mean for that. All right, couple more questions. If someone, maybe you, I don't know, were wanting something that was streamlined or aerodynamic, what are you trying to avoid when you have something that is streamlined or aerodynamic? Like a really go-fast car, or a go-fast bike, or a go-fast boat. What are you trying to avoid? What do you want to do? You can write down what the object's made to do, or you can write down what you're trying to avoid, because that's what they're made for. Good. All right, that was a long one. I wrote down a couple of things. Streamlined objects are meant to do what? They're meant to go fast. Those really fast motorcycles, people don't get them because they want to go slow. They want to go fast. The second thing is they are trying to avoid something we call drag. Drag is the air that we walk through all the time. There's always drag on our body because there's tons of air around, and that's a good thing because we breathe this air. So it's something that we have to have. Unfortunately, for people that like to go fast and like to avoid, air when they're driving, it's something you can't escape. That's why people make smaller, lower to the ground cars, is so you can go fast. You avoid the friction of the air. Unfortunately for them, you still have friction with the tires on the road that causes you to slow down. So there are other factors involved, but taking something and making it streamlined or aerodynamic does add a little bit of resistance. I mean, it lessens the resistance on the object, okay? And then Mr. Murphy showed me a really cool video yesterday. It wasn't aerodynamics, but it was hydrodynamics, how people swim. And I'm actually gonna show you guys that video probably next week. It's a really cool video about how this one guy started doing his backstroke, and he ended up, I don't know, what did he get, second, Murphy? He got silver, I think? Did he get gold? Yeah, so he won the gold medal, and he had such an unorthodox way of swimming. I'm gonna let you guys see it because it almost seems like it should be illegal, but it's not, because he's technically swimming. So, all right. Now, yesterday, we talked about this word acceleration. Now, I know some of you guys at home didn't get this same lesson. I think some of you guys were definitely logged in for it. Well, we talked about acceleration a little bit, and acceleration is a bit of a touchy term, man. It's kind of tricky to talk about. So what we're gonna do is I'm gonna try to give you some other examples. Now, how they got the word, if I can ever find it, how they got the word accelerator for this thing is probably because they knew you were gonna have to build up speed over time, all right? Because everything on Earth has to have some sort of acceleration in order to move. Things just don't move by themselves. You know, this isn't some kind of haunted house or anything. Things have to have a force to move, okay? Whether it be the wind, an earthquake, whether it be something accelerating an object, okay? So we watched the first Eureka video on acceleration. Now this is the second part today, and it's pretty good. I really like using this video because it shows a really great example of what accelerating is and it gives you a cool little picture to look at. So we're gonna watch this, and then we're gonna talk about friction. All right, because we've got a lot to talk about, obviously. All right, Gage, you have a question, young man, on acceleration?
Acceleration and gravity.
All right, well, ask one of them, dude.
Not less gravity. So when you're skateboarding and you go down half pipe and you're in the air, how would gravity work for you when you're going back down?
Okay, so this is a great question. Gage just asked. Gage is a skateboarder, so Gage is riding a half pipe, all right? And I am going to show you a picture of a half pipe. All right, since none of you guys know, maybe, it's half of a pipe, right? Can't skateboard a whole pipe, at least Mr. Allen can't. So a half pipe is gonna look a lot like this with skateboarders on it, okay? And I know that's not the best drawing, but this is really quick. So Gage is on a half pipe, and Gage is gonna go down and go and bust the air. And what'd you say? How does gravity?
How would gravity affect you when you go down? So would you get gravity, like would you get your balance back with the board as soon as you hit the ground?
I don't know. Gage wants to know how gravity is gonna act. Well, would Gage ever land if there were no gravity? Yeah, if there were no gravity, like let's say Gage went down the ramp and came back up, and then all of a sudden gravity got cut off, where would Gage go? Gage would be going up to the space, all right? So in order for him to do this half pipe, he has to have gravity. Now, unfortunately for some skateboarders, they come down a little bit too hard because gravity is very unkind to people a lot of the time, especially when you fall off your bike or anything like that. So these forces have to be had, and that's why everything starts making sense when you have gravity involved and friction and things like that. Gage, we'll talk about it in a minute, buddy. Now this second video of acceleration is pretty good. I'm a big fan of it. So let's go and let me make sure I've got the right one. All right, hold on one second. All right, here we go.
Eureka! The story so far. The greater the rate of change of speed, the greater the force required. Another word for rate of change of speed is acceleration. The more you accelerate, the more force you need. But force also varies with mass. So we say that force
Mr.
equals
Allen?
mass times acceleration.
Yeah?
Turn it up more.
Yeah, I'll do the best I can, bud. Hold on one second. And then we're gonna have some pitfalls, bud, so we're gonna try to figure all this out.
Or can you put it closer?
You need to move it closer? I don't think it's
Yeah.
gonna go any closer, dude.
Because it has a.
All right, let's try that. I'm gonna go close this window.
Acceleration. And now, acceleration part 2. How do we measure acceleration? That's one way. But there's a better method.
So why is he holding up those clocks? How do you measure acceleration?
Time.
By time,
Time?
right? Yeah, you're doing it by time. I mean, think about it. If I told you it was gonna take me an hour to get to Raleigh, okay? How long is an hour?
6 minutes.
I don't want to. Never mind. I don't want to go over that yet because that'll kind of ruin my lesson.
Oh, you see, most things do all the accelerating they're going to do in a matter of a few seconds. So it isn't very practicable to measure their increases in speed in kilometers per hour. Take this locomotive, for instance. It's a very old steam engine, and it can only do 36 kilometers an hour. But it's
36 kilometers an hour. So how far can this thing go in an hour? 36 kilometers, right? Well, it's going 36 kilometers an hour, KPM.
acceleration is surprisingly good. It can get up to this speed in only 10 seconds. Yes, it is impressive. But can you answer this? How far will it have gone by the end of the first second? Or by the end of 10 seconds? Give up. That's what comes of mixing speed in kilometers per hour with time in seconds. We've got to reduce it all to seconds, and we'd better reduce the kilometers to meters as well while we're at it. The train's top speed is 36 kilometers an hour, which is the same as 36,000 meters in an hour. Since an hour contains 60 minutes, we can divide 36,000 meters by 60 to find out how many meters it goes in 1 minute.
Now it says it's gonna go 600 meters every minute. 600 meters. So let me tell you how far 600 meters is, okay? 600 meters would probably be about 7 times around our track. Okay, so do you think this train, when it starts, is it gonna go 600 meters that first minute?
Nope.
How many of you guys think that it is? Raise your hand at home or in the class. How many of you guys think it's gonna go 600 meters the first minute it starts off? Good. It's not, because it has to start first. And starting something large takes time. Once again, I'm gonna use me and Mr. Murphy's little prime example. Mr. Murphy, a lot smaller than me, he can get off the line a lot faster than me. And I'm gonna be a little slower, but who's gonna have more power? Me, because I'm way more massive than him. So there's pluses and minuses to speed and how long it takes something to get there. But let me get back to the lesson. Let's keep going.
Then we divide again by 60 to see how many meters it'll go in 1 second, which comes to 10 meters in 1 second. So we now know that 36 kilometers per hour is the same as 10 meters per second. That means that once the locomotive has reached its top speed, it is covering exactly 10 meters of track every second that goes by, never less and never more. But remember, this is speed, not acceleration. Acceleration means that with every second that passes, the train advances an increasing number of meters until it's eventually moving at a speed of 10 meters per second. But it didn't start out that way.
Okay, can y'all see the very bottom part of this track at home and in the classroom? Can y'all see that?
A little bit, it's kind of fake.
You can? Okay. Now, what we're about to do is they do a really good example, and that's why I love watching this video, is because it does such a great example of showing the train accelerating. And you're gonna see that the little man is gonna pop out a little blob of bubble gum or something out on the track. And you're gonna see this progression of these cones or this bubble gum getting further apart each time. Because every time you start to walk, every time you start to run, I know that you think that you're going as fast as you possibly can, and you probably are trying, but you all have to try to build up speed. And like someone like myself, it takes a while to build up speed because I'm a lot bigger. I got a lot more to carry than somebody like Mr. Murphy. Mr. Murphy doesn't really have to build up that much speed because he can get out off a little bit faster. He's a little bit smaller, a little bit more streamlined than Mr. Allen. So I'm gonna stop this a couple of times. I really want you guys to notice the cones that the train is dropping off, okay? And I'm going to slow it down and go over it.
Ready?
Okay, so this is the beginning of the train ride where he's gonna pop down. So he's gonna throw out a cone right to begin with because he's starting to move.
You've got 10
So
seconds
pop
in
one
which to
down.
attain a speed.
Okay, now we can already see at the beginning, that's the first one he knocked down. That's the second one. That's the third one. So what are you starting to see between those just 3 little blobs, Gage?
They're starting to get further and further apart.
They're starting to get further and further apart, okay? And the reason he's doing this is he's throwing down a block every second, okay? He's throwing down a block every second. So this should show you that every second he's getting a little bit faster. Now, what's gonna happen over like 10 or 15 seconds? What's gonna happen to his speed? Like Usain Bolt yesterday, when I showed y'all that, his first 2 or 3 seconds of that race weren't as fast as his last 7 seconds. Why? Why was that? Somebody besides Gage. Aiden, how about you, buddy? Put that calculator down.
We have a couple hands in here.
Yeah, Alexandria, let somebody in there answer, because Aiden was playing with the calculator.
Porter and Addison.
Porter, go for it.
she said it takes it takes a little bit of time for them to go fast. And then what did you say about 15 seconds? They're not going to what? I'm sorry. They're not going to be able to see the one that they placed down before.
Okay, that's possible. That's definitely. What about you, Addison? What do you think?
It takes people time to accelerate speed if they don't have a lot of math.
All right. Well, let's keep going. All right. We'll ask this question in a
meters
minute.
per second.
So now,
Very good. Now let's replay that and analyze what happens.
all right. Here comes the explanation. So y'all pay attention.
In the first second,
So the first second, he is going to throw down a block.
you reach a speed of 1 meter per second.
He's going 1 meter per second. Is this 10 meters per second? No, because he's just starting out. The acceleration is beginning, okay? But he has not reached the top speed yet. 1 meter and 1 second. That's not good, okay? That's way off of our mark of 10 meters per second.
And cover a small amount of railroad track. In the second second, you reach a speed of 2 meters per second.
So look at this right here. He starts right here. He goes to there, goes from there to there. There is a slight difference. Not much of one. This is where we're going to see the big jump.
And cover a larger amount of track. In the third second, you're going at 3 meters per second and cover.
Okay, This is where you see the big jump. So you can see he's starting to pick speed up. Now when he starts going at a top speed, there's my mouse.
Covering yet a longer stretch of track.
So this is
and
after
so
3
on.
seconds.
By the end of the 10th second, you're going at a steady speed of 10 meters per second and covering 10 meters of track during every second that passes from then on. Your acceleration is over. But how much was that acceleration exactly? That's right. Your locomotive increased its speed by 1 meter per second, every second. In other words, your acceleration was 1 meter per second, which physicists like to write like this. And that's how you measure acceleration.
Now listen, you do not have to remember that for acceleration, but he showed in that he went 1 meter per second for 10 seconds, and it took him 10 seconds to get to top speed. The acceleration took him 9 seconds. So for you guys yesterday when we were watching Usain Bolt, it took him about 2.5 to 3 seconds before he got to full acceleration. He didn't start off that speed. He had to build that speed, just like everything on Earth, right? Because we have something called air that slows us down. And we also have friction. When Usain Bolt was sitting there running, think about the friction that his feet are on when he's going on down the track. Think about the railroad. Think about the locomotive on the railroad tracks. They're going down tracks. I know that they're nice and smooth, but there's still a lot of friction. And think about how big a locomotive is. Think about all the air it's trying to go through. So all of those factors factor into the acceleration, to the speed, all these things, okay? It all plays a huge role. Now, acceleration, I'm gonna go over again next week along with the word momentum, because these are two words that when they throw them on a test, they can get a little bit dodgy. They're a little bit tricky because they try to trick you. That's what their job is. I got about 8 minutes, and I want to show you this video that I've shown probably since this happened, because I thought it was a really, really cool thing to talk about. Come on, dude. Are we frozen? Come on, man. Give it 1 second. There was a meteor that hit Russia, and I'm not sure what year it was. I think it's probably about 10 years ago. I don't know what's going on with my computer. Here we go. There was a meteor that hit Russia about 10 years ago. And let's talk about a meteor's life, or we could call it an asteroid, whatever you want to call it, space rock, all right? Well, in space is a very, very different place. Is this the right one? Should be. Oh no, that's the Go Fast cars. Hold on, we're not gonna watch that one. How to? Where is that? What on God's green earth? Where'd that thing go?
When the only thing that matters is being together.
Hold on one second, guys.
Holidays to a Vrbo vacation home, somewhere with more space to get even closer to the people you love.
This is what happens when you got too many windows open, guys. Man, I'm gonna have to show that to you later because I don't understand where that video when I had it up.
Might have cleared it out.
Did I?
Yeah, I think so.
Let's hit the back button.
Yeah, you probably accidentally clicked it and then it left.
Cars doing donuts. I don't know why I did that. That's crazy. I had the best video. Oh man, that stinks. Hold on one second. I want to show this video. Yeah, I want to show this video. Let me see if I can pop it back up. I don't know what in the world happened. I guess me and Aiden were talking about it and here we go. All right. Now what this is this is a news feed, okay? And I don't think it's from Russia because they're speaking American. That's why I know it's not from Russia. But this is a video of a huge asteroid that came, or whatever you want to call it, meteorite, whatever you want to call it, that entered Earth's atmosphere. And I want you to think about the life of an asteroid, okay? Asteroids or space junk or space rock come from exploding stars, you know, or maybe bits of moons that have fallen off of planets, or moons out in the distance. And once they fall off, since there is no friction, there is no air, there is no drag in space, they just float. And when they're floating, they start to rocket through space because they're going super fast. When something blows up, that rock is going to be put out in such a forceful way that it's going to shoot off in all the directions, okay? And that space rock is going to go through its life without encountering air for a long time. Well, think about how big space is. They got the name space because there's a lot of space in space, right? So once this thing, you know, exploded and this asteroid was born, it never encountered air. It's never encountered friction its whole life. It's just kind of like floated through the air. Well, sometimes when things get a little bit close to our gravitational pull, they can hit us. And this is, you know, the claim of the dinosaurs, you know, millions of years ago, that this huge asteroid came and put up this huge cloud of dust and killed all the plants, and then all the plant-eating dinosaurs died, and then all the meat-eating dinosaurs died because they didn't have anything to eat. It was a huge cyclical thing, and this is like a theory that they've thrown out, and there's actually proof that this asteroid did hit, and it caused one heck of a crater. Now, this one didn't cause a huge crater, but it did cause a little bit of damage. So I'm gonna let this play, and then we're gonna talk a little bit about it. I'm gonna pause it a couple of times.
Debris from the meteor racing toward Earth, streaking across the sky there, crashing into the ground in those woods. And look at some of the other images emerging.
Okay, so that is a huge smoke trail. And that is not from an airplane. That is from this meteor coming and hitting the Earth. Now, why would this thing put out smoke like that? I mean, when I look at them at night, it's like, whoa, cool. There's a light trailing this cool meteorite. And it looks like it's got a tail on it, right? Why would this thing smoke like that? Aiden, Michael.
Because of the friction, just because of the little atoms.
Yeah, excellent, dude.
Because of
Aiden,
atoms.
Mr. Michael got it right on the money. The asteroid encountered friction for the first time in its life, and what does friction do to all objects on Earth? Slows them down and heats them up. And I can tell you right now that this meteorite definitely slowed down. I mean, there's no telling how many thousands of miles an hour it was going when it was in space. I think that would be almost incredibly difficult to calculate. But when it hit Earth's atmosphere, since it hit air and it started going through our atmosphere, which is those 5 layers, it started to slow it down. It started to heat it up and it burned up. And so we got really lucky, man. I wouldn't say us, Russia, they got really lucky that this asteroid did burn up, because when it hit the lake, it was probably about 12 feet in diameter. It was big. And if it would have hit land, it could have caused a lot of trouble for some people. But I want you to see what it does. The force of just this rock hitting Russia. And this is hundreds of miles away from where the rock hit. Watch what it does to these buildings. And this is like a long way away from where the meteorite hit. So there's a lot of forces at play in this. And we could talk about this video for a long time if we wanted to, but we're not.
Tonight, the cloudy trail the meteor produced, and on impact, this.
So there's the impact of the crater. So you can see it probably about as big around as the room, the classroom, which if it would have hit land, it would have really caused some trouble. I'm talking like it would have shook the earth probably. It would have, I mean, I don't know if it's that big, but it would have shook Russia really well. So just watch what happens.
Carving a little.
And I don't know what they're saying because they're speaking Russian. I'm sure they're scared to death though. I would be.
Pool into a frozen lake. It's the biggest meteor in more than a century to hit the planet. This one crashed in Russia. 1,000 people were injured from shards of flying glass and debris. Tonight here, we have learned there was no warning. More on that from NASA in just a moment here. But we begin with ABC's Kirit Radia in Moscow.
Beware, a bright speck in the sky.
So that's where the burn up starts, right when it hits the air. And you can see the trail. And that's not light, it's just smoke being illuminated. Okay, so that's the burning up. As soon as it hit, like that outside troposphere, not troposphere, I'm sorry, the outside thermosphere started to burn up immediately, which is really lucky for us. Well, for Russia anyway.
Sky soon crossed the horizon, followed by a most apocalyptic scene, a blinding flash of light, and then all hell broke loose. Dizzying explosions, shattering windows, knocking these office workers to the ground.
So look at this, look at the force. Blew all those windows out.
Curtains from the flying glass, and these men barely escaped the blast. In the streets, pandemonium. Terrified residents thought the world was ending. People started to panic. Somebody screamed, "The end of the earth," he says. The chaos of the meteor was captured on cell phones and on dashboard cameras of cars, so popular here in Russia. The blast was so powerful it knocked down a wall at this factory. In all, over 1,200 people were injured, mostly from broken glass. 3,000 buildings damaged, over 1 million square feet of glass shattered. Many were injured after going to the window to check out the flash in the sky. The glass shattered and bounced back on me. My beard was cut open, this man says. The meteor was believed to be about 50 feet wide, weighing a whopping 7,700 tons. That's about the same as the Eiffel Tower. It raced towards Earth at over 40,000 miles.
So there we go, 40,000 miles an hour. That's almost as fast as Mr. Murphy in the 100-yard dash. Not quite though.
Per hour. As it crashed into the atmosphere, it began to break into pieces, causing those booms and sending those powerful shockwaves towards the ground, rocking a zone stretching hundreds of miles away, those shockwaves causing all of the damage. As for the pieces of the meteor, one of the bigger chunks landing here, leaving that massive hole in the frozen lake.
And that's not the whole meteor. That's just a piece of the meteor. So that was a big meteor, man. They got lucky.
Tonight, about 20,000 Russian troops are headed to the affected area. They'll be helping those residents who are struggling without windows. Temperatures are expected to drop well below zero overnight. Meanwhile, Russian television coverage has been going wall to wall with what some commentators said looked like a scene out of an action movie. David?
Okay, so we can watch some more of that later, but I got to stop. I just want to explain to you real quickly, and then I'm going to let Ms. Moore have her time. This is something that if it would have happened here, it would have caused a huge ruckus. People would have thought that it was the end of the world because you look up and you see a big stream of smoke, and what do you think somebody probably fired at us? Yeah, a nuclear missile is what I would think if I went outside and looked at that. But what I want you to think about until we get back next Monday is just the sheer power of just a rock coming and hitting the earth. And those buildings that had all those shattered walls and all the shattered glass, they were hundreds of miles away from this meteorite. And if you want to think about what 100 miles is, think about driving from here to Raleigh. That's 120 miles. So you do that up and back, and you got about 240 miles. If a meteorite hit Raleigh with that kind of force, we would probably have a lot of broken windows down here, and it would shake the ground. And the thing hit the lake. It didn't even hit the ground. The pieces hit the lake for the most part. So that is an incredible force. And unfortunately for us, they have people working at NASA. Aiden, Michael, you could probably do this. They have people working at NASA right now, 24 hours a day, 7 days a week. And all they do is look into a telescope into the sky, and they look for meteorites coming to Earth. They can see many, many thousands of miles into space. I don't know how. These telescopes are amazing. They can see them, and sometimes they miss them. They missed this one. They did not see this one coming. And it's really difficult to see them during the day because think about it. If it's not illuminated, if it's illuminated up in the sky and it's the middle of the day, you can't see it. You usually see them at night because you can see the trail of them, you know, in space. But this is a really, really, really crazy event that happened. It was a while ago, but just remember, this could happen anytime, anytime. So, you know, count your lucky stars that it didn't happen. All right, you guys are good. Y'all have a good day. I'm gonna try to upload this lesson, guys.
Hi guys, so there's a poll on the team.